funciona o top. I would say good morning, but let's be honest with ourselves. Morning is not good, right? So, hi. Morning. Now let's go for our last lecture of the series. We have gone through a lot of work to be here. Now we have learned a little bit about the theory of the standard model, a little bit on how to design a detector and how does it, how a detector actually works, in the sense of how you can actually use macroscopic matter to detect microscopic particles. We have seen a bit of how to reconstruct the data, how to take out the data from the detector and put it in a reasonable way that you can understand. And now finally it's time for fun, for some values of fun, yes. But we start doing the data analysis. In very broad terms, you can divide the, let's say, data analysis in two camps, okay? Either you're measuring something that you know exists and you want a better measurement of it. For instance, you may want to measure the mass of the Z boson or the coupling of the Higgs boson to the other particles to see if it's on top of the predictions of the standard model. Or you can search, where you try to uncover some evidence of discrepancies between the standard model predictions and observed data. And this includes everything. This includes search for new resonance, supersymmetry, dark matter, strings, you name it. But in a sense, this distinction is a little bit arbitrary. We do it nonetheless, but it's a bit arbitrary. Because consider, Higgs to mu mu at the 13 TeV LHC, okay? The Higgs couples to the mass of the particles. That's why when you are searching for it, in the production, one of the big channels of production is gluon-gluon fusion, coupling to the Higgs, and then it decays on whatever it has to decay. How can it couple to the gluon if it couples to the mass and the gluon is massless? The answer is that this loop process with the top quark here is responsible. Yeah, but it's a loop process. It's a higher order of perturbation theory. It doesn't matter. This coupling here is so strong because the top is so heavy that it's enough to overcome the fact that it's a second order effect. Other ways of producing the Higgs boson would be vector boson fusion. So you have stuff like WW coupling to the Higgs, and then the Higgs decays on whatever it wants. Same way on the decay side, by the way. One of the decay channels of the Higgs is to diphotons. Now I'm going to draw it here. I'm going to concentrate the loop into a point. In the same way, the Higgs couples to the top loop and to diphotons in the final state, even though the photons don't have mass. But it, of course, also couples directly to particles that have mass. So what does this have to do with anything? Higgs to mu mu. The muon has mass, but it's tiny compared to these other particles. So the cross-section of protons to Higgs to mu mu is small. It's something on the order of 12 femtobarn. For setting the scale, remember that during the whole run to 2016, 17, and 18, we took something like on the order of 100 inverse femtobarn of luminosity. It was 137. So let's round it to 100, multiply by this cross-section. And that means that during the whole of 2016, 2017, and 2018, we produced more or less 1,200 Higgs bosons that decayed into 2 muons during the whole of the 3 years. So more or less 360 whatever days per year. It's 1 per day. And then you have to detect that guy. So it's really, really tiny. Bottom line, we didn't find this thing yet. But it's still a standard model. It's still a prediction. We want to measure it, but we didn't find it yet. So we still call it a search, just like we were searching for the Higgs boson before discovery. On the other hand, if you're searching for a new resonance, say, PP going to Z prime, going to EE, 2 electrons, so a new Z boson, Z prime boson, we usually make a lot of assumptions on the value of its mass, spin, blah. Usually we would say that we are calling it a Z prime boson because it's a spin 1, it would be a spin 1 particle. It would be a new gauge field. And then you search for a Z prime of 1 TeV, 1.1 TeV, 1.2 TeV. And then we try to measure its production cross-section. When we are searching, we're trying to find something like this. You have here the peak of the Z. This is number of events. This is the dielectron mass. You have the peak of the Z here somewhere, around 90. And then you are searching for new peaks around here somewhere. Since you're trying to measure its production cross-section, the thing is that usually we come up with a value which is statistically compatible with 0, so it's not there. But what do we actually measure in the end? And this is something for which we have an easy answer. We count the number of events in a given configuration. And this given configuration is your analysis. So for the LHC, PP, proton-proton, 13 TeV, center of mass, with this configuration of a trigger, so we have some pre-analysis done. With this configuration of the detector, I ask for events that have such and such and such characteristics. And these such and such characteristics may include falling into a given beam of a histogram. And then I count how many events I observe. And this is the master equation. I like that sentence. And this is the equation for the number of observed events in a given configuration. It has at least these 4 factors. We can unpack them a little bit. Sigma is what nature gives us. It's the production cross-section. This is purely theoretical driven. This is the thing that you calculate with Feynman diagrams. L is the accelerator luminosity. I didn't speak much about accelerator luminosity in the second lecture as I wanted, but suffice to say that it's how many particles the LHC can fit in that interaction point at a given time in a given time in that given space. If we manage to remember that I said that it's 1 proton per cubic meter, the region that LHC manages to compress the proton cloud. Ideally, I would like to make it even more concentrated. And that would make this luminosity here number. And this would make this luminosity number here go up. Or I would like to make these bunches come faster. And then again, this would make the luminosity go up. It would also have the problem that we would have multiple interactions happening at the same time, and this would be complicated. But the point is, this is accelerator-driven. This is actually what we pay the LHC guys to do. A is the acceptance. It measures for a given process the ratio of detectable particles that actually go into the detector volume. So this depends on essentially how well do you manage to cover the detector point, the interaction point with your detector. In an ideal world, I would like to cover it all, 4 pi. Of course, it's impossible, because at least you need to have the hole through which the particles come through. But as I showed you yesterday, besides sensitive elements in the detector, you also need to have the scaffolding, the hole where the cables come through. No, we cannot do wireless. But people thought about that one night in the cafeteria. The technology is not there yet, but people are seriously considering it. And epsilon is the selection efficiency. It's given that nature has given you these many events, sigma times luminosity, and some of them went into your detector, how many of them do you actually reconstruct and get into your analysis? And this can be subdivided into 2 parts. This first part is the efficiency of reconstructing a given set of objects in the detector. This is what we talked about yesterday. Given that there is an electron going in my detector, how well do I reconstruct it and am able to use it as an electron? And this nomenclature is completely ad hoc. And this epsilon A is the efficiency of any further requirements that I do in the analysis. So in the case of the Z, I would ask, oh, and I want 2 electrons that have this much energy, at least in this region on the detector. They have to be opposite sign. They have to be same flavor, 2 leptons or 2 muons. Or this is where my imagination comes in. This is the fun part. Now, the given configuration we discussed is determined by this acceptance and efficiency. Everything before depends on nature and depends on the accelerator. I start from sigma times L. I strive to maximize for acceptance and efficiency. And now, the actual total number of events that we observe in that configuration is a sum over all the physics process. So it's a Z, but there may be a Z prime contribution or something else that also gives 2 leptons. Anything that really gives 2 leptons plus fakes. And fakes can be anything you can imagine. It runs over, and we are going to see examples, it runs over the most strange things. For instance, cosmic rays going through your detector, they can go through the detector, and it looks like, if it crosses through in the right direction, it could look like 2 muons, but it's actually only 1 coming from the sky. It's a fake. Longitudinal particles from beam interactions. The beam is going, for some reason it's not well collimated. It hits some element, and some particles come flying through longitudinally. Beam. You have some kind of signal on your detector, which is a fake. Hardware failures. Hardware fails. Sometimes your colorimeter cell turns off permanently, or even worse, turns hot permanently, always giving a very high signal. Software failures. Sometimes your reconstruction software fails miserably and tells you that there are 1 billion tracks in this particular region of the detector. This actually happened to me. And even for the fun stuff, the phase of the moon. But Thiago, how can this is all true, okay? Then you download these lectures and click. How can the phase of the moon give events on your detector? Come on, my geophysicists, that some of you should be, right? Statistically. What's the phase of the moon correlated to? Sure, gravitation, of course. Now on Earth, what does it mean? Tidal forces, exactly. So tidal forces means that the configuration of your accelerator changes ever so slightly according if it's a new moon or a full moon. And this configuration, changes the initial configuration of the beams, and you can see that on the accelerator, not in LHC. It could have been seen on LAP. The seasonal variation of rainfall, same reason, because of the seasonal variation of rainfall, that means that the ground, it changes its properties subtly, and that's enough for it to move the accelerator a little bit. And again, it changes the initial configuration and changes the number of events you observe. The schedule of the French high-speed rail trains, the TGV, Train Grande Vitesse. This one, it was not because it would move the ground. It was even better. There was I don't remember if it was capacitive or inductive, but there was a long-distance coupling in between the current of the lap and the current of the magnet that would bend the beam and focus the beam. And then, but it was like a clock. The TGV arrived, they saw the beam energy changing. And all of these are actual effects that were published here. Please take a look, it's very funny. Bottom line, you may not know what's affecting your physics effects. You may not know what effects is affecting your physics. Sure, you start with the easy things first. So I'm not going to talk about that except to draw attention to it. But start with collision processes. Start with real backgrounds to your search. But at some point, you have found if you have found a significant effect, you have found it. Now you have to search to see if it's new physics or if it's actually striking the TGV. Going back to collision process. Remember, the fact is that the sum goes over all physics processes. We cannot readily separate the process in which we're interested. In the case of the Z, sure, you're asking for 2 leptons, but you cannot ask, oh, and give me 2 leptons that come from the Z. You don't have access to this information. This information, nature just gives you whatever it's giving you. It doesn't, you cannot tag the electrons from their parentage. You can ask for 2 electrons, and then you can try to separate what you're interested in. But this you have to do with the final state particles and the quantities that you are able to understand from the final state particles. In the case of the Z, it's absolutely obvious, but we'll see some other examples. We're going to see one big explicit example in the end. Backgrounds are, again, separated in 2 kinds. Either irreducible backgrounds are those that have exactly the same final state. The Z to leptons is one example. PP to gamma-gamma was the one that was extremely relevant a few years ago because of the Higgs boson. If you have 2 photons in the final state, you have all the other contributions, and particularly you have the PP to Higgs to gamma-gamma. The final state is exactly the same. You cannot disentangle them. So you have to estimate the whole spectrum and try to find a little bump on top of it. And that was exactly what is done. But sometimes the final state is the same, is not quite the same, but enough. For example, if you're searching for ZZ to leptons to quarks, so something like this, which could be coming from a new resonance, new physics, one background to this search, this has 2 leptons and jets in the final state. One background to this search would be inclusive Z2LL production with next to leading order corrections of QCD. It's complicated, I don't understand this. Let's look at the diagrams. So, this is right? Yes, I hope it's right. Nossa, mas aquela luzinha está bem diferente. This is Higgs going to gamma-gamma. And here, sorry, there should be, now I see what's wrong. Here there should be a blob as well, of course. And this is the signal process we're interested. And these are 2 of the QCD processes that act as the background. This is Born and Box diagram, we call them. You cannot readily disentangle the contributions from these two from this one. Here on the bottom is the same thing. You can have some new physics process that gives two leptons to quarks. And this is a possible background. The difference is that, oh, here you may have one jet, while here you have two. But this mapping of gluons and quarks to jets is not one-to-one, okay? It's approximate. So it may be that this guy more or less gives you the same number of jets as this guy here. But then you can try to use some other variables to find out, to disentangle the two of them. And this is the job of the analyst, to try to find variables that separate signal and background. So you search for, go ahead. You could, like, this is not a irreducible background because the final state is not the same. Like, it's not, it has a glue here. A glue is not a final state. Remember, the glue radiates and showers and hadronides. The final state here would be leptons, do two leptons plus jet. The thing is that you cannot distinguish easily in between these jets that will come from this leg here and this jet. And remember, there can be another gluon coming out, or this gluon can split into two quarks, and it will, actually, of course. Now, it may be that for some configuration, you manage to cut out the contributions from this guy, but not all. It's a bit, actually, I don't think this example was that good now thinking about it. But reducible background is where there is some difference that you can leverage to try to reduce it. In the case, for instance, of Z2LL, it's trivially simple. What if you have the dileptons? And we can even start before. You have everything. What do you need to do to search for Z2LL? Well, you need the leptons, so you need two high PT leptons. Why high PT? If you assume that the Z boson is produced at rest, like it usually is, usually means the highest cross-section of it being produced is it being at rest. It has 90 GeV. That energy has to go somewhere. What usually would happen is that it will go to the leptons. So you have leptons with high energy, and high transverse momentum as well. Flavor is conserved, charge is conserved, so you would ask for two same flavor, opposite charge leptons. And then you ask for the invariant mass. You take the four vectors of the two leptons. You measure it. Remember, measure the energy, measure the momentum. You have everything. Sum the two four vectors, make the invariant mass. And you know that the Z is already 90 GeV, so you ask for it to be in this range, 70 to 110. For instance, okay, it doesn't matter that much if you change this a little bit. 90 just has to be in the middle. Beam, look at this. You have only the Z. It's done. Actually, 95%, right? Because you can see here that there is a background subtraction applied here, but it's extremely pure. Or it can be extremely complicated. On the bottom, you see something that's called the razor variables that are used for supersymmetry search. Essentially, the idea is that you gather everything that happens on two sides of the detector. You call them the mega jets. And not a joke, this is really how we call it. And calculate MR and R square, which MR is given by this complicated expression here. Notice here that it's really the absolute value of the vectors of the first and second megajet, and then the absolute values of the Z component. No, not the absolute values, then the Z components. And then the transverse R mass, which again is this complicated expression here. Notice that it involves the PT means. Why does it involve the PT means? Because supersymmetry, in this particular flavor of supersymmetry that we're searching here, is that particular kind where there is something called R parity that is conserved, so the neutralino is stable, is neutral, and escapes your detector. It's just like a neutrino. So this is that kind of supersymmetry where you always have missing PT. And you calculate these two guys, and of course here it's obviously the plot is horrible. But what you do is that you compare the data with your background. In the data, obviously the points. The background here is the field histograms in a lot of different regions. So each one of these big regions is one bin of the histogram of one of the variables. I think it's MR. While the small bins are bins in R square. It's a complicated way of doing a two-dimensional histogram. The guys who run this analysis think it's easier this way. And then at each point, you compare the expectation with the standard model expectation with the observed data. Who came up with these variables? Who invented this guy? I wish it had been me, but it was a friend of mine who's the guy's amazing, and one day was thinking really hard, and found out that these would give the best separation, and they would also be robust against undetector mismeasurement. Because remember, if half of your detector turns off, exaggeration, if there is some mismeasurement, there can be some fake missing PT. But this variable, the way it's constructed, is robust against most kinds of mismeasurement that can happen in the detector. And then it became the standard for supersymmetry searches for almost 10 years now, of this particular kind. But of course, sometimes you don't need to think hard at all, right? That's what, when the robot revolution comes, it doesn't matter. Now we have machine learning. We don't need to search for the variables. The computer can do it for us. So machine learning is becoming a tool in the toolkit of every high-energy physicist. And the advantage is that it's really good at it does. For instance, if you want to separate signal from background, it is amazing. The problem is that you don't know what it's doing. But it works wonders. I'm not going to speak about machine learning, except to tell you that you can apply it to two kinds of problems. Either you classify your samples. So for instance, you ask your machine learning algorithm, is this background or signal? And it answers. After some training and all you have to do the machine learning, you have to take your algorithm, train it, teach it how to do the separation, and then you let it loose on real data. And then it's obviously useful, right? Because it classifies the event as signal or background for you. It gives a yes or no answer. But in the backstage, it's actually working with a variable. So sometimes we unpack, go one step behind, and instead of working with the binary classifier itself, we work with the discriminant. That's what's been shown here. This is the output of a machine learning algorithm applied to one particular search. I think this is supersymmetry as well. Supersymmetry as well. We have no idea whatsoever how it builds this ANN discriminant. But what you can see is that, no, sorry, this is not supersymmetry. This is TT bar H. Yeah, it's written there, sorry. This is this process here, which is also difficult to find. I think it's this, the diagram, okay? Yes, it should be something like this. Gluon, giving T bar, and remember the Higgs couples well to the T, so it's kind of like a Higgs stratum here. Super small cross-section also. And you can see here, it's very difficult to see, but try. In this variable that it built, look, the light blue here on this side, all the background, all the signal clusters on this side here. And you see that the data is slightly more compatible with this, with the light blue being there than not being there. So it helps us find the signal, which is the light blue. What's the problem? The problem is that we have no idea what this A and N means. It's just a number in between 0 and 1 for us. On the other hand, you can also use it for regression problems. So instead of asking the classifier for a binary, for the machine learning algorithm for a binary classification, you ask it to help you fit something, to do some regression. And we use it, for instance, to help reconstruct the energy of a B jet, a jet which has been tagged and has a B hadron inside. And it's slightly better, for instance, for finding the correct mass of the Higgs boson. See, in red is before using the machine learning algorithm, and it doesn't quite peak in the right place. In blue, it's a little bit better, plus it's a little bit, the variance of the distribution is a little bit better. Is this an immense amount of progress? No, but then you combine this with other measurements of the mass of the Higgs boson, and you have something in the end. Then fine, you're ready. You have found your model, you know what you're searching for, and now you're going to start designing your analysis. Welcome to the fun part. You're going to design some set of cuts, design some set of selections, dilepton, invariant measures in this range, PT above this, eta in between this and that. But you have to be careful. Here are some guidelines that they give us, for instance, CMS. First, you want to be unbiased. In the medical science, you want to do something that's called a triple blind study. What's a blind study? It's a study where data is temporarily withheld from some set of people. A blind study is the one where in medical, okay, you blind the patient. You don't tell them if they're taking medicine or placebo. Placebo is like when you give them the sugar pills. Why is that? Because placebo effects exist. If you give somebody a sugar pill and tell you, no, this is medicine, you're going to feel better. Psychologically to work, and they will feel a little better, even if you give them nothing. So you don't tell them, if you're testing for the efficacy of a new drug, you don't tell them if you're giving them the real thing or placebo. Here we particularly don't have this problem because the protons don't care. But then there is double blind. Double blind is when you are asking the patient, so how do you feel? The way you ask may have difference, may have a measurable difference. If you ask, are you feeling well? It's different from asking, are you feeling bad? It's just like when they do another simple example, when they ask for the popularity of a given politician, the way you phrase the question is important. Because then you can prime the person who's answering to answer in this or that way. And in the case of energy physics, the person doing the asking is us. This is what's called the observer bias. And again, it's measured, it's true. What we do is that we design the whole analysis before looking at the data. We design with simulation, we design it with control samples, just like they have control samples in medicine, we also have them too. We design the whole analysis and freeze it in place. And only then we open the box of the data. There is also a third possibility of blinding, that is having separate sets of people that design the analysis and who run it. Because then you will have, besides the observer bias, you have the experimenter bias. Again, in medical sciences, they do this. The people who run the tasks are not the same people who interpret the output of the tasks. In high energy physics, we don't do that, mainly probably because we don't have the person power. But what we do is that we freeze completely the analysis, including the post-blinding resolution. So we try to follow what the protocol we set before in order to minimize this bias. So these are some things that you have to be careful. Second, okay, so you're cutting. You're asking, oh, the dilepton should be this or that. And you must not blindly follow a recipe of maximization. There are some recipes on how to choose your cuts, but you have to think a little bit in the sense that, oh, I managed to maximize some figure of merit that I'm using. Unfortunately, that means that now I have 0.0003 signal events and a background of 0.000000007. Which I hope that, of course, if you have a Poisson distribution with this mean, we are going to see 0 events, but then you actually learn nothing. It's not that with 0 events you learn nothing, but if you expect 0 signal in 0 background, why the hell are you running the experiment then? You have to not be dumb when making the optimization. Which ties to the third point. You have to study the marginal effect of each of your cuts by tables and plots. What do I mean? What do I mean? You have to know what each of your selections is doing. What is this cut doing? Oh, dilepton mass in between 70 and 110. Oh, that's actually cutting this region here, and I know that this region is enriched in Z. Oh, that cutting missing ET. This is helping me kill the instrumental background because low missing ET may or may not be related to a detector effect instead of a real invisible particle leaving the detector. You have to check the before and after of each of your cuts. If you actually do everything right, and then what you should finally do is plot or make a table, but of the efficiency of your cut as function of your parameter of interest. What do I mean by this? So here you have, is there a question? Sorry. Here I show the efficiency of my selection. This is actually one of the analyses I worked on. I actively worked on. There are 2 branches of the analysis that we call merged and resolved. Merged and resolved, it just means that, merged means that it was this, okay? Merged means that these 2 guys appear as one jet. Resolved means you actually see 2 jets. Only that. And they were split categories, right? Like beans in a histogram. Events that were in one category were not in the other. So here you see the efficiency of the merged untagged, the green line here, and you see that started low and then stabilized in a value around 40%. 40 to 35, let's say. Is this good? Is this bad? From my point of view, this is amazing. It means that for every signal event that nature is giving you, okay, for every 10 signal events that nature is giving you, you manage to save and put in your histogram 4.5 of them in average. You're losing a lot, yes, but the background, I managed to kill 99.99% of the background. I arrived at this set of cuts using an optimization, but with some constraints in order to avoid being in this kind of situation. And then I designed some other set of cuts that were disjoint, exclusive, to help cover this little region here, where the mass of the resonance was searching for low. So here it's not so great, but here instead of searching for 1 jet, I can search for 2 jets, and it's this red line here, which grows faster, but then it starts falling down and asymptotically to 0, and it helps cover this region a little bit more. Is it perfect? No. Here, when the mass of the resonance was so low, it was still close to 0. But then somebody else in CMS could also be doing an analysis there. And then maybe we could combine later. So you managed to design, run your analysis. You have some events. You have not looked at them because they're still blind. Because what else do you have to do? You have to estimate your background. Is this? No. You have to estimate your background. So you optimized it already, but some background always remains for some values of always. Even if it doesn't, let's say that, now let's make something reasonable here. Let's say that after you optimize the thing, we ended up with signal equals to 5 and background equal to 0.2. This is amazing, okay? This is like you're in heaven. It may be small, you may end up having 0 background events, but then what? You need to put an uncertainty in whatever number you're predicting. If you're predicting 0 background events, you better find a way to put an uncertainty on that 0. And it cannot be 10% of 0, which is also 0, okay? You really have to have a real uncertainty. There are some ways to estimate the background that remains. First, you can fully trust the simulation. Run the Monte Carlo, run Giant, run your analysis on simulated data, count. This sucks. Why? Because we don't usually trust the simulation. We want to trust real data. Simulation gets it wrong. It's NLO, NLO, and NLO. We don't care. But it's not the real thing. Plus, all of those detector effects that I talked about in the second lecture, they're super hard to simulate correctly. They're easy to simulate good enough, but do you want good enough for your analysis? So it's not recommended. CMS actually won't allow you to go through it, except maybe for backgrounds that are so small that even an error by a large factor would make no difference. If you actually have another background here that is 100, and this is more or less what's actually about, fine, I mean, do whatever you want for the 0.2, it doesn't matter. What we can do is to data correct some of your simulations. What do? You define some control regions, control samples, where you expect a similar behavior of your background. So your background is supposed to look the same, both where you're searching and where you're doing the control. But where you're controlling, you have almost no signal. How do you do this in practice? You invert one of the cuts, or you look in a variable that's not the one you're searching for. It's related, but it's not the same. And there you check that your simulation is working well. And if it's not working well, you derive some correction factors. And with those correction factors, you go back and correct your data, your simulation. You never, ever, ever correct the data. The data is king. A third option is to model the background in situ, which is more or less the same, but your control regions will be at the same time measurement regions for some other modality of your search. I'll show you now. Go ahead.
I don't understand why do you have to simulate the background, because you said that for example, if you use machine learning, it will classify the event as background or signal.
Yes.
And then you already have your number for background from the data, doesn't it?
First, it will tell you that these events, let's say you have it doesn't matter if it's a machine learning algorithm. You have something, which is either an analysis or a machine learning algorithm or whatever, and it tells you that from these 100 events that we started with, 10 of them are background, and 10 of them are signal, and 90% are background. Now, your standard model prediction is that you would expect 95 background events in this region. Have you found new physics? Can you go to Stockholm, collect your prize? If standard model would say that there are 95 background events. You actually observed 90 events of background plus 10 that you think are from signal. Is it true? Probably, probably. Actually, sorry, by the way, this is bogus. What I really mean, sorry, not 90. Of course, you have to compare with this 10. So there are 10 events that you think they are signal. Standard model tells you that there are 7. Let's make it hard. 7, there are supposed to be 8 remaining signal events. 8 remaining background events in this region here. So the 8 is to be compared with the 10. So do you believe that your machine learning or your algorithm missed 10 of them, made a mistake in 10 of them, or are irreducible? Or actually there is 8 background events and 2 true signal events? You have to estimate what you expect to compare with what do you see. And by the way, go ahead.
How do you know from a measurement, how do you know, for example, why are there 90 background events? So how do you measure the background?
That's the problem that you have here. You have to solve this problem. So either you trust the simulation, you run a theoretical calculation, run it through the simulation detector simulation, and count the numbers. You may correct it, checking that your simulation works in some other control samples, or you try to measure it in situ, for instance, which is what is here. Here, this is the dijet spectrum, okay? So you take the two jets with most energy in the event and make the invariant mass. QCD, quantum chromodynamics, predicts that this thing is smooth. I am searching for bumps. I'm searching, there may be a coloron or a graviton or God knows what, and then I would expect to see a bump. You can in situ do an interpolation, let's say, between this region and this region and try to predict this region here. And then you do this for every small window. And now I'm telling you, this is equivalent of asking, is this function smooth? Can you fit it with a simple exponential-like thing? Or does it need to have a bump? This is how you can estimate it directly from the data. In some other cases, for instance, here, this is the search for one of the searches for dark matter. You help correct your simulation from a control region. For instance, this is the Z2 electrons control region, and this helps you tune and correct your Z2 electrons simulation, which by flavor universality, Z2 neutrinos should be more or less connected to Z2 electrons. Then it comes and helps you here predict the green histogram here, which is Z2 neutrinos, which is a background to missing ET to the search for dark matter. Because Z2 neutrinos is invisible, and so is the search for dark matter. So is the dark matter. So each of these colored histograms here is tuned in a control region like this. Is it more clear now? Go ahead.
Why do you trust your predictions? I mean, isn't that similar to trust the simulation?
One thing is trusting blindly, is just running and not caring. But here I'm trusting but verifying. I'm doing my best with the predictions. I'm doing my best here. And if it doesn't work, I derive correction factors from the data, and so data is king. And then I use this corrected simulation to predict here. And then it's fine. And you can also have corrections, for instance, theoretical. Actually, while I was doing this, somebody went and calculated the NNLO thing. I can also use that. But in the end, you do use the data for guidance. The best thing in the world is to use only the data, but sometimes that's not possible. More questions? I know that this is complicated, so thanks for going and asking. By the way, sorry, I accidentally flashed the next slide, right? So you saw what is coming. You knew it was coming. All of these questions are probabilistic because all of these All of these are random variables, so we have to use probability. The question, I expected 8 background events. I observed 10. How compatible is the 10 observed with the 8 expected? One part of the problem is finding the 8 expected, find that the number is 8. And this is estimating your background. The other thing is, okay, given that I expect 8 and I observe a 10, what does it mean? And that's a probability question, so let's go for it. I assume that all of you have had some training in probability and statistics, but I find it useful for us to go through a little bit. What's probability? There are many different answers to this question, okay? And it was only formalized by Kolmogorov. I don't know if it was in the last years of the 19th century or beginning of the 20th, okay? I don't remember. Probability is something simple. Probability is something that obeys the Kolmogorov axioms. It has to be positive for all possible events, where event is something that happens. And the probability of, sorry, this is wrong here, of xi or xj is the sum of the probabilities if they are exclusive. So it's either this or that happens, xi or xj, but not both. And when you sum the probabilities of all possible events, it has to go to 100%. Mathematically, it's simple. Unfortunately, that doesn't help us with anything. But it's important to keep in mind, because now let's go for something that can actually help us. Frequent twist probability. You observe n events, big N. You observe small n of a given kind. For instance, I flip a coin 10 times and I observe 5 heads. What's the probability that any single event will be of type X? What's the probability of flipping a coin, it will be heads? You take this limit. It's the limit of the frequency. And this is what we learned in our first statistics course. Oh, but Thiago, you cannot do this because you cannot actually take the limit to infinity. True. I don't need, right? Remember, for instance, when we studied electromagnetism, the electric field, we started defining it by taking a very tiny charge, another one charge, and one test charge, and you made this test charge so tiny, and you used it to measure the Lorentz force, the electric component of the Lorentz force, of this, that this small charge would fill. And then you could you defined it as, it's the limit of the test charge going to 0. First, nobody actually does that, right? Second, you cannot because charge is quantized. So the least you can have is 1 electron. And nobody cared. We all continued working with the electric field, so on and so forth. Here's the same thing. You don't need to care about the limit going to infinity. You just make n as large as you want and take that as a good approximation for your probability. There are some problems, though. First, these experiments, they have to be repeatable. And what does repeatable mean? Sure, if I flip coins many times, it's repeatable. But if I flip coins tomorrow, is it the same? Yes, but why? Because I know that shouldn't matter if I'm flipping coins today or tomorrow. So repeatable doesn't mean exactly equal. It means that all the relevant conditions have to be the same. Science should have reproducible results. Guys, what's the frequentist probability of raining tomorrow? The question doesn't make any sense because there is no repeatability. There is only one tomorrow, right? So for some questions that we want to answer, what's the probability of rain tomorrow? It's important. I need to know if I have to take out my umbrella. Frequent twist probability doesn't help. Enter the Bayesians. Bayesian probability is the degree of belief in X, whatever X is. It may be a model or a hypothesis. What's your degree of belief that the sun will rise tomorrow? Mine is close to 100. I'm not expecting the apocalypse anytime soon. So there is an operational definition given by Finetti, which is a coherent bet, which can read from here. The idea is that if you follow this degree of belief, and it's complicated, right? Because belief seems to be subjective. Maybe you're actually somebody who believes the apocalypse will come tomorrow. But if you really believe, you should be willing to bet on it. With this definition here, you can show that the degree of belief follows the Kolmogorov axioms. And if it follows the Kolmogorov axioms, it's good enough for me. It's probability. However, there is a problem. It's subjective. Again, if I believe that the apocalypse is coming tomorrow, I estimate that the probability of the sun rising tomorrow is close to 0. So it depends on both the observed and observed system. And it will change if I obtain more knowledge. It's subjective. And this is a little bit problematic for us as scientists, right? Because we would like to be objective. We would like the data should be king. Whoever does the analysis, it doesn't matter. It matters that it's done according to scientific method. On the other hand, really, there are some questions that do not have an answer in frequentist probability. Is the universe cosmologically flat? You saw that in the cosmology lectures. Because that determines the final fate of the universe in a sense. What's the probability that the Higgs vacuum is stable? I'm going to talk about this in one slide. There is no probability. Either it's stable or it's not. Either the universe is going to end or not. You can talk about probabilities of random variables, of random events, but not of facts of nature. What's the probability of the electron charge being this? There is no probability. It either is or isn't. There is something called objective Bayesian statistics, okay? And there are very good guys working on it. But the science is far from settled, and I'm not going to speak more about Bayesian, except to keep it on the back of your mind. This is what I mean by the metastability. This is funny. So if you make a plot of the top quark mass and the Higgs boson mass, you run the renormalization group, it turns out that for some values of the Higgs and top combo, that potential that used to be like this, except that spin, right? It can become like this or like this. And what happens if it becomes like this? What happens if there is no true vacuum? The universe may be unstable. And we are just one phase transition away from something else, but probably not good for us. Turns out that if you run the calculations, that remember the renormalization changes the constants, in a sense, changes the constants of the Lagrangian, so this may happen. Turns out that we're right here, it seems. Right in the region of metastability, which is surprising. This plot actually is much larger, okay, for different values of the top mass and different values of the Higgs mass. And this yellow part is actually just a tiny slice, and we're right there. What's the probability that the universe is stable? Even if you don't buy into Bayesian statistics, one thing's true. Bayes' theorem is true. For discrete events, probability of A given B, and this is what's called conditional probability. Given that B happened, what's the probability of A happening? It relates to the probability of B, given that A happened, times the probability of A happening divided by the probability of B happening. Now, I'm not going to prove this theorem, but if you're a frequentist statistician, I have to go a bit faster, you can only speak about random variables here. But if you're a Bayesian, you can speak. What's the probability of this parameter of my model, for instance, the mass of the Higgs boson, given that I have observed this data, is equivalent to this. It's the exact same thing, just changing the names. But in the Bayesian framework, you can speak of the probability of a constant of nature being something. Or if you go to continuous random variables, the probability density function of a constant of nature. What is the PDF that the charge of the electron is in between, alpha, of course, right? Is in between 138 and 139. Blah. In frequentist statistics, you cannot do that. Now, let's go just for continuous variables, okay? It's just a simple jump here. I'm going to call it probability, but it's really probability density function. You integrate these over some parameters to actually get a probability. This is a PDF. P of theta giving x is a PDF. It's the posterior probability density for theta. This is what I'm interested in. Is my parameter in this or this range? This is the likelihood function. Given that the parameters are these, what's the probability of observing this data? But if you run the numbers here, it turns out that if you run the dimensional analysis here, this term is not a PDF. The things in the denominator don't really mind. They are sort of normalization constants. And here lies the problem. What's the prior probability density for theta? What do you believe before running your experiment about your parameters? You're going to search for supersymmetry. What's your prior belief in supersymmetry before running the experiment? It's probably different. Yours is probably different from yours, probably different from yours. Are you people going to give me different answers, even if you're looking at the same data? And here lies the beef, right? That's the big problem with Bayesian statistics. You have to somehow address your priors. Here's an example that will drive the point home. These are stored straight from Wikipedia. So there are two species of beetle, the common and the rare. Now, the rare is only 0.1% of the population. I go and see one beetle that has this pattern X, maybe it's some dots in its back. In the rare one, 98% have the pattern. So most of the, I don't want to change to English the thing. 98% have the pattern. The probability of having the pattern, given that you're rare, is 98%. But if it's the common one, 5% have the pattern by random happening. Remember, the rare subspecies accounts for only 0.1% of the population. So it's really, really rare. I found one that has the right pattern. How likely is the beetle having the pattern to be rare? I found one. Is it rare? Of course, if you run the calculation, you find the Bayesian answer. Does anybody want to guess? Order of magnitude. I found one. Is it rare? Should I write a paper? Give me some number in between 0 and 100% that you think is right. Oh, maybe 50%, right? I mean, 98% of the rare beetles have the pattern. What are the odds of me being on the wrong, of me being on the 5%? Let's call it big. Let's call it 50%. Turns out that this is what's called the base rate fallacy. If you actually run the numbers, turns out that with these inputs here, even 1.9%, even if I found a beetle that has a pattern, it only has an actual 2% chance of being a rare beetle. Because we're starting from a very high, very lower base rate. Remember, only 0.001% of the beetles are rare. And so Bayes' theorem is true. But you have to, if frequentists want to interpret in terms of only frequentist probabilities. But then you have this problem that you don't have not the mathematical framework, nor the philosophical framework to define the probability of a parameter of nature being true. That doesn't exist. It's not a repeatable experiment. It's not a random variable. It's a number. Unfortunately, people fight. So if you need, in Bayesian statistics, you need priors. And then the physicists complain. But the fact that you don't use priors in non-Bayesian statistics makes some statisticians complain. And it's a fight. So, of course, we make jokes about it, right? You can read the joke yourself, but the idea is that if you're a frequentist, if you're a true to the heart frequentist statistician, in this situation where you have a detector that checks if the sun has exploded, but it rolls 2 dice, and if you have 6-6, it lies. And the detector actually tells you, yes, the sun has blown up. If you take statistics, frequentist statistics seriously, you should bet that, yes, the sun has exploded with 95% confidence level. Of course, you can use a little bit of Bayesianism. Remember that your prior for the sun exploding is small, we hope, and not take this bet. Sorry, you should bet on the other direction. How do we solve it? We don't. In practice, we try to find methods that are okay from both sides. It's impossible to reconcile both in a coherent way. But you try to give practical answers to your statistic questions. So again, I expected 8 events. I observed 10. What does it mean? So you can estimate a parameter. And what you do is that, remember the likelihood that I spoke just a little bit ago, which is proportional to the probability of having observed that data given the parameters. If you actually do maximize the likelihood, you will find the best estimate of those parameters. And then it's really this, okay? It's just that, but you do it numerically. And it can be proven that this is optimal for large n. And this will give you the best possible estimate for a parameter. If you want instead to answer the question, find the range theta A less than theta less than theta B that contains the true value of the parameter theta 0 with some probability. For one-dimensional, it's trivial. There is a super simple recipe. For ND parameter, use something called the profile likelihood, which is yet another application of the likelihood. How does this work in practice? Here's again another result that I explicitly worked on. At some point in both Atlas and CMS, we're seeing some deviations of the standard model predictions that seem to indicate that a new particle existed with mass of 1.92 TeV around that would decay into Ws and Z bosons. Unfortunately, the signal for Atlas was very strong. It was like a big bump, while the one for CMS was more subtle. And the question is it compatible? How compatible is it with the standard model? And what's the best estimate for the cross-section of this new process, assuming it exists? Then what we did was we combined the likelihoods, profiled. I'm not going to go through that, but the point is that we combined the likelihoods, and we found that the best value for the cross-section, assuming the new particle existed, was 5.3 plus 2.3 minus 2.0 femtobarn. This was of the round 1 data up to 2012. And then it would have to be checked with the next data. It wasn't there. Which brings us to hypothesis testing. How do you actually choose? How do you actually go and ask, okay, I observed 10 events, I expected 8. Is it standard model or is it something else? This is what's called hypothesis testing. So you define a new hypothesis. For instance, it's a standard model. An alternative hypothesis, it's actually SUSY, supersymmetry. You have different likelihoods. And what you do is that for the null hypothesis, so that means assuming, oh, sorry, this was supposed to be the same H0. You define a criteria of extremeness, which for the purpose of this talk, I can say, oh, how high can I fluctuate? How high can I fluctuate and still be compatible with the standard model? Sure, if I observed 15, if I expected 8, and it's Poissonian, right? So it goes more or less, the uncertainty goes more or less like square root of 8 in this case. It's not exact, okay? What's the probability of fluctuating up to 15? It's more or less 1, 2, almost 3 sigma. Quote unquote, okay? There is a right way to do this. This is with my hands. You order all the possible observations from the most extreme, oh, I fluctuated a lot, to the less extreme, oh, I fluctuated almost nothing. And then you have to decide where you put your cutoff, some smallish number. Oh, I want to reject all, you choose this before. Oh, I want to reject all explanations that require that I fluctuate more than 95% probability. And then you actually go and observe. And then you reject the null hypothesis if what you observe is in the most extreme fraction of observations. I'm going to show you the plot, it's easier. And then you have to define, and then you have two probabilities. The probability of rejecting H0 when it is true, the false discovery. I say, oh, it's Susie, and then you miss because it's actually the standard model fluctuating a lot, versus the probability of not rejecting H0 when it is false, is missing the discovery. Oh, it's a standard model. No, turns out there was supersymmetry there, and the other guys found it before you. Sucks to be you. And then you have to balance those two things. How do you choose in which values for alpha and beta is also a matter of debate. But that's what you have to choose. This is the example for the CMS measurement of the spin, of the parity of the Higgs boson. Assuming that's a scalar, does it have positive or negative parity? So again, here, it's one parameter only, right? It's only the parity. So it's a one-dimensional histogram, and you order them from more to less extreme. And then you put a cut around here somewhere of alpha, and then you check and then you check the observed one. Let's say you put the cut at 0 for some purposes, okay? This would be a very big alpha. You observed it, and it was more extreme than the one you are accepting, than the one you are willing to accept. So you do not reject the null hypothesis. This is mathematics, but if you look at the plot, what it means is, if you had to bet that the red arrow that you observed comes from the yellow distribution or the blue distribution, which one would you bet in? Still, this is not a complete decision. You cannot just from statistics, either frequentist or Bayesian, you cannot decide, oh, am I going to call a discovery or not? It still requires a prior belief in which one in the two hypotheses, and standard model is usually well regarded, and the cost of making a false discovery versus the cost of missing a discovery. In high energy physics, we go with 5 sigma criterion. Oh, if the result you explained, if the result you see would be observed only by a 5 sigma fluctuation, then you will call a discovery. But this is completely ad hoc. Okay, it's Bob Cousins, which is the resident physics statistician, the message is without foundation. Unfortunately, I'm still positive that this will be used until the end of the let's see. And now, super quickly, let's go through a single analysis all the way, okay? Let me take just a bit of water. Let's suppose we are in lab and trying to measure the number of colors. Now, in this region below the Z resonance, so below the Z peak and lowish energies, And assuming that all quarks hadronize, you can show that the ratio of electron positron to hadrons over electron positron to muons goes like a number of colors over sum of the charges of the relevant particles, which in the end turns out, you can run the calculation, 11/9 times the number of colors that exist. So this is an okay way of measuring is a reasonable way to try to measure the number of colors. And these are the diagrams, okay? Why? Because if there are more colors of quarks, instead of red, green, blue, you have whatever, fuchsia, there will be more diagrams of this kind. So the number of E plus E minus hadrons will increase. This is the idea. How do you measure this? This ratio is proportional to the number of colors, but this is a ratio of cross sections, which don't have access. But you can divide the actual number. Remember, number of events is sigma times lab times cross section times luminosity times efficiency. So here you can divide both by the luminosity, and this is the true number of hadronic events and leptonic events produced. Now you only have to measure these two numbers of events, which is easier. Then you have to find your variables and start trying to separate hadronic events from leptonic events. One possible thing is that to count the number of tracks. Usually leptonic events have fewer tracks than hadronic events. So you optimize these, you cut, and you say, okay, all events that have less than these tracks are going to call leptonic. All above, I'm going to call hadronic. First, there is an overlap, of course. So there is an efficiency to select a given kind of event, which means that we should correct the number. What comes here is the number of true events. But I measure something with some efficiency, so we should correct. So we should estimate these efficiencies. There are other efficiencies, right? There is the acceptance, again, all the things that we spoke about, the trigger efficiency, the efficiency of actually reconstructing the tracks, of managing to take the data, and the efficiency of your cut. So in practice, what we will do is that we would correct for all of that, and for the fact that there is some background still remaining after you cut, and get the true number of leptonic events and the true number of hadronic events. And then all of these are observed values, so you have to do error propagation, so on and so forth. In the end, you make the fraction, and for this region of square root of s larger than 10, so all the quarks contribute in all of their colors, but you want to be below the Z boson peak. And so you want to be on this region here. Why not here? Because here some other quarks do not contribute, because the square root of the available energy is not enough to, for instance, create quark of that flavor. What are these peaks? These peaks, they are they are resonance. This simple picture of sigma of two hadrons over sigma two leptons is spoiled when you have the creation of resonance. When you don't have resonance and when you have all the quarks available, you are in this region here. And then you can measure, and it gives you more or less 11/3, which means that you have 3 colors. This is how you would do an analysis. Tools of the trade. Root is good. Root is nice. Root is everything there is. Everybody in high energy physics uses root, either willingly or unwillingly. For good or for bad, it's going to be with us until the end of the LHC. It has everything. It has histograms, plotting, fitting, statistical tests, how to make a website, 3D plotting. Root has everything. An alternative that's coming up, it's not in general. SciPy is a Python-based framework instead. Root is mainly C++. SciPy also has everything, but it was not ready when we started designing and running and constructing and running the LHC. Now it's in a good shape. I'm actually using SciPy for my latest analysis. But the key point is that it's Python, and Python is very good to interoperate with the machine learning machinery. So I wouldn't say use it, but I would say try it at least, because machine learning is really the hot new thing that's going to eat everybody's lunch. Which brings me to my conclusions. The field is about trying to understand the most basic constituents of matter. It's one of those, it's a nice field where theorists, experimentalists, computer science, and engineers all manage to work together and make things happen. It has had extreme success in the form of the standard model, and people keep searching for extensions of the standard model to find new, to try to explain new effects that come from other fields of physics, cosmology, astronomy, and so on. From the experimental side, due to the fact that, what I talked about in the second lecture, you need large accelerators, you need large detectors. We have moved to the big global collaborations, and that means also big data, right? We are the original big data with the petabytes and exabytes. And it's also big in the time scale. We started designing the LHC in 1989. And by we, at that point, of course, I don't mean myself. I was 6 years old. So it takes time to run. So it needs long-term commitment. It will run until more or less 2035. And then who knows what the next experiment will be. But we have to start thinking about it now and designing it now and trying to find the funding for it now. And with that, I would like to thank you. And remember, we need you, okay? We are completely in need of people. So if you have been interested by these talks and want to learn more and maybe come to work for us, we're open for business. So go to our website and contact us. Thank you very much. Because the last one, because they are too low, the energy is low enough, so there is no energy to make a top quark pair. Not on purpose, right? Nobody wants to cheat. But sometimes people do something that is kind of not correct from that point of view without knowing, and then you have to decide. People decide to, there are even accidents. People unblind themselves earlier. They forgot to turn off the parameter, show the data, and it happens. How to treat that depends on what happens. Sometimes if you just accidentally unblinded yourself, just look the other side and redo, doesn't matter. It's more interesting when you actually unblind and you see a huge discrepancy, and then you say, this is impossible. If these were true, the supersymmetry would have been found in 1989. And then you remember, oh, of course, I forgot to add this background, which is 10 times more important than anything I thought. How do you deal with that? Be blind, not stupid. Of course, if you made a mistake, a real mistake, then go back to the beginning and undo it. There is not a problem. More subtle things is what's called flip-flopping. If you do if you try to measure something and you don't manage it, you set an upper limit and say, okay, this cross-section should be lower than this. If you do measure it, then you put, and that's a one-sided limit, right? You say, oh, it has to be larger than this. If you do measure it, then you're putting a two-sided limit. And you're saying, okay, so I measured it and its value is in between this and that. If you are not careful on how you decide to do this switch, and that's why it's called flip-flopping. You go in between the two options. You may end up in a situation where you say, oh, this arrow bar, which is supposed to mean the 68% confidence level, right, is actually less than that. Because you followed a statistical procedure that in the end gave you a different coverage. Coverage is important. And then you'll be lying to whoever is reading your paper. This used to happen a lot until we got Bob Cousins to hit us all with a ruler in our heads, telling us the right way to do it. These are subtle questions, okay? But it used to happen, now it happens less.
We have seen the whole process of conducting the experiment, reconstructing the data, and then analyzing it.
And simulating. Theory is also important.
How much time does it take, this whole process?
More than I'd like. From when you decide to start working on an analysis until you actually publish the paper, I would say on the order of 1 to 2 years. But that's the thing, right? That's why you need a lot of people working on running the data, and you can parallelize. That's the other reason why we need 3,000 people in this collaboration, to make the best of all the data.
As far as all the computational procedures we have seen along these lectures go, to date, what are the bottlenecks so far as computational time?
Today, there are the main bottleneck is the simulation. All those interaction of radiations of matter that I spoke about in the second lecture, they take more or less 1 minute per event. And we need billions of events. So we have a grid, we have big computer clusters all around the world. We divide the work, and we manage to simulate all of that in more or less 2 to 3 months, depending on if there is summer or Christmas in between. But this is going to change with the high luminosity LHC, because there the events will be so complicated, because there will be 200 simultaneous proton collisions at the same time, and then you have to connect the dots. And right now, the answer is because the latest estimates, never quote me on this, puts the reconstruction time for one event around 1 hour. And we will have billions of those events. That's why I said we need something smarter to do the high luminosity LHC tracking. Because this is real. With the technology we have now, it's impossible. So again, either Intel does a miracle, or we make a miracle. And that's why I'm actually running machine learning to try to see if I can make something better or different. That's going to be the computational bottleneck.
In the same line of thought, is there any hope that quantum computers can help improve this kind of processing?
I would shelve that under the label miracle. Yeah, but yes. But now the question comes back to you. Are we going to have quantum computers that I can go to Kalunga and buy the... until 2026? No, right? So, oh yeah, and they have to cost $500 per computer, which is our budget. I know that some of you have questions, but you are way too shy to ask. Go for it. Now is the time.
So you said earlier that we will probably use the 5 sigma limit, the cutoff
Mm-hmm.
for the data. So what would be the alternatives?
It's easy to criticize. It's hard to actually find an alternative. The point is, it depends, as I said, on the how well do you weigh the false discovery against being scooped. And does the 5 sigma actually protect you from that? Or does it protect you from mistakes? Remember when the Opera experiment wrote that paper about neutrinos flying faster than the speed of light? And turns out that it was mostly a loose cable. But by the way, this is not piling dirt on the Opera collaboration. They did an amazing number of checks. They did good science, and they released their results for the world to double check. After all, extraordinary evidence means extraordinary claims need extraordinary evidence. How many sigma did they have? Now, on the other hand, the muon, remember I spoke about the anomalous dipole magnet, anomalous magnetic dipole moment of the muon. There is a gigantic discrepancy there. Nobody is speaking about it, right? So we are just like ostriches putting our heads into the sand. Why? So the answer is it depends, and it has to depend because you have a prior. You cannot get rid of the prior. Even if you try to be fully frequentist, you by yourself, your reasoning as a person is in a sense Bayesian. Even if I came to you with a 10 sigma effect in the Opera experiment that told you, no, but really, neutrinos fly faster than light, you would still be searching for the loose cable. So it's an open question.
Are there often false discoveries?
Yeah. Well, so after we crank it up the discovery to 5 sigma, no. But when we start, there was a case with Leon Lederman, who went on to discover the big quark, that prior to discovering it, he found a bump, a resonance in the wrong place. And it was just a statistical fluctuation, but if you looked at the plot, it really looked like it could be something. There was a peak, but it was a statistical fluctuation. And of course, it was a flop. And how do you protect against that? One way that the community seems to have found out is to use 5 sigma. I don't know where the number 5 sigma came from. One thing that I have heard in CMS is that if you run 100 searches with 100 beans, each in the histogram, the chance of finding a 5 sigma distribution is a 5 sigma fluctuation is more or less than finding a 3 sigma in one single search, in one single bean. And 3 sigma is what we use it to call evidence. We still call evidence. But then where the number 100 searches, 100 beans came from? From somebody's pocket, yeah. So there used to be at least one, and seems that it burned us bad enough.
Some time ago, I heard about measurements at the electric dipole moment.
Electron dipole moment, okay.
Electric dipole moment. That suggests the electron is not a point-like particle.
Mm-hmm.
It has not with spherical symmetry, at least.
Okay, I get it.
So where it stands right now?
No, I'm sorry. There is search for composite electrons, non-point-like electrons in CMS, but in Atlas. But as of right now, there are no conclusive evidence for the electron not being point-like. This experiment we're talking about is probably from low energy. It's probably interesting. Something like that would be, again, revolutionary, but I don't know where it stands. Does anybody know? Okay, we search it later. Next.
When you were talking about statistics, you gave us a way to compare the standard model and some competing models.
Hypothesis testing, yes.
And do you know if there are any competing models that are being well succeeded in experiments, or you're only confirming the standard?
So in high energy physics, again, except for these cases where for some reason people are not speaking about, but it's complicated because, again, it's a low energy measurement, not high energy. Low energy, and then you have to take into account a lot of factors that are non-perturbative, and it's a mess. In high energy, as far as I know, the standard model has been not falsified again and again and again and again and again. It's starting to be boring. But there are these bumps, right? And then people write papers about them. Some of you might recall the diphoton particle at 750 GeV. And it was a small bump at the diphoton spectrum, 750 GeV, that was seen both Atlas and CMS. So it seemed it was there. And people wrote many papers about that. The theoreticians literally went to town. And turns out that it was a fluctuation in both experiments at the same time. Now the new fad, but this one I trust a bit more, is something called RK star, which is something to do with lepton flavor universality, and this has been seen by LHCb. And there are, again, some models that try to explain that. But up until now, it's not conclusive. Coffee? Yeah, I'm interested in that too.
So what did you say? You said that someone has found one, or that there's
I
constraints
just
on it?
heard about the lecture some time ago, but I didn't research very long about it, so I don't know what state the results are right now.
I know that
If there are
there's constraints on the existence of one.